Okay, welcome. Let's look at shift registers. Obviously, we'll start with the left shift. There are three things that you must note here. Okay, first of all, the data has to go in at the right. Okay, the data has to go in at the right. It has to go in at the what? At the LSD side. All right, and it will obviously LSD. If I write a number, if I write a number, obviously the LSD is going to be what? The one that is at the right. All right. So therefore, the data goes in from the what? From the least significant digit side, and to what? Second thing that you have to note, it will glide. The number will glide towards the what? The left. All right. It's a left shift, so things are shifting to the left. All right. Towards the what? Towards the MSD. All right. Obviously, if that's the case, it means that the what? Just take a number, for instance, the MSD will lead. Let's take a number 10, e.g. let's take e.g. an example, e.g. 1011. When you are done, the number must read 1011. All right, okay, these are binary numbers, right? When you are done, the number must read 1011. Therefore, what does it mean? It means that this one, the MSD, will have to go in first, followed by that, and they're all going to us. When you are done, as they move, this is moving towards being the what? The MSD. So the MSD must go first, followed by the second most significant, all the way up to the least. Okay, so they'll follow each other in that order. 1 will go in first, followed by 0, followed by 1, followed by 1. All right. Let's draw a 4-bit what call shift, left shift. Or these are simplified version now, just to explain. The diagrams are going to get a little bit more, or maybe fancy, as we progress. So first of all, remember, not always, as long as we are what, as long as we are dealing with what, with shift registers, we are using D-type flip-flops. Okay, D-type, okay, or other configured as a D-type. Okay, configured as such. I'm writing a reminder here. I've mentioned this before. Okay, so it has to be or configured. Okay, so it has to be, in case this comes into clash with my diagram, let me move it a little bit. Okay, please note that we are going to use D types, or any, if you are going to use an SR, it has to be configured as a D type. If we're going to use JK, it has to be configured as a what? As a D type. All right. So, well, the T type is not configurable as a D type, so we can't use that one now, can we? So right now, then what we then do is our input, remember, goes in through the D. So this is where our input will come in. All right. This is what we'll call it our series data, because it's going to follow, the bits are going to follow each other what? One by one. Okay. Let's say series input. All right. So it comes out at Q. What does it do? It is going to enter the next D. So when data comes in here, it comes out there, it enters the what? The next one comes out, enters the next, comes out. So obviously enter the input, these are inputs, comes out on the output queues and enters the last one. All right. If we have more, that one would have gone to the last one, but that's our Q8. That doesn't stop being our Q4. That's still our Q2, and this is our Q1. All right. So now we remember now is you have to be careful which type of what, which type we can use. A what? A clock that tells us that the what, we are just using a delay, or we can be using the type that is what. I'll come back to that now. Let's have a clock. So our clock can be direct like this, in which case we know we are using what, we are using leading what call this, the leading edge of the clock. Our clock can come direct like that. In this case, we remember, oh, I want that to be neat, in which case we'll be using the leading edge. Okay, so it depends on the type that we're using here. We're using a delay edge here. Otherwise, we can be using a what, a master slave, of which we'll use a what, a trailing edge. In this case here, we're using a leading edge. If it's like this, this is what, It's leading edge. We've dealt with this. It could be, the alternative is what? The alternative is if we're using, okay, we could be using, instead of what? We could be using symbol like this. This symbol means we're using what? We are using the trailing edge, which means it's a master slave. Oh, okay. This would imply that we're using a, not trying to take it too long, so I'm not going to be what? I'm going to fuss about little things. So now, oh, did you not have a Q there? All right, now, so look how the clock is common. Why? When there's new data coming in here, at the same, all four must open at the same time. So I'm using what? A synchronous clock. So new data is coming here. What needs to happen is that what? That they all need to open what? Whatever is waiting at the what? At the entrances, at the inputs of each must be allowed through. So they will all let data go in, pass through at the same time. So this here, if we are using, remember we could be using the what? Without the little inverter here and the arrowhead here, and it could be direct like this, or if we are using the type that we just said now, then obviously it is using trailing edge. Oh, okay, it's grouped together. Let me first ungroup it, ungroup, then I can now say if it's like this, then it will be using a trailing edge. But I think this, at this point, this should have been discussed enough for people to follow what I'm talking about. So you have to be careful which one is what. Remember, one option, let me rather put it on the side so people don't forget. One option is for your clock to be like that, in which case we are using a D latch, and it's what? It's using leading edge. Okay, or the clock can be, let me remind you that this is a clock. Okay, or the clock is sent through this here. This could be our clock, or that could be our clock. Okay, in which case here it's a master slave, and it's obeying or responding to the what? To the trailing edge. So it could be leading edge or trailing edge. You have to be careful how it's done there. All right, we'll deal with both cases when we're doing the timing diagram so that people know the difference. Now remember that when you want to put new data, it is always good practice to clear out first, though it will still work even if you didn't clear out, but there'll be no harm if it's not cleared out. It will still work. It doesn't depend on being cleared out, but we might just want to clear whatever data was there initially. So with there, reset. So with reset, quite frankly, we some things are not necessary to show. I mean, this is the what? Reset data, and remember we reset with the what? With the 0. In this case, the not Q is redundant. It's not like we have. Remember, this is a flip-flop. This is a complete flip-flop. So by default, it has a set data, but because they're redundant, there's no harm in leaving that. Even though some might fuss and worry about maybe needing to show the not Q, but it's redundant in this case. It's not going to work. So there's really no harm in not really worrying about it. Okay, if you're going to do it, then you have to be consistent. Okay, but you see, I've left the what? I've left the reset. Not that doesn't exist. The set data. Not that doesn't. It's not there. It is there. Our symbol is not complete without it. But sometimes when we're drawing, we're just drawing for to show knowledge. So this is a redundant part of the what of the symbol. So sometimes we just leave it open. We might have left the not Q open as well. There'll be no harm. Now, when we have this now, what is the difference between, I mean, our input is going to come in here, so our output, our series output is going to be coming at the end of the what? Of the register. So this will be our series output. It will come out where? At the highest at the what, at the MSD. Okay, to come out at the MSD. Remember, this is our 2 to the power of 0, which is our LSD. This is our 2 to the power, the highest. In this case, we only have 4, so this is what, our MSD here. Okay, this will be 2 to the power of 3 in this case, but there could be more depending on how many bits you're actually dealing with. So this information can also be read out there as a what, as a parallel. Let me rather, I've got so much space down there and I'm getting so much traffic at the top. Okay, there's no need to save space and lose marks. Okay, let's make our diagram nice and clear. All right, so now you can see we can take out our parallel output at the top. Let me rather ungroup this because sometimes you forget and it becomes a hassle. Parallel output can be read at the top. Parallel output can be read at the top. What does it mean? It means I must have one clock pulse to pass the first digit, second clock pulse to pass the second digit, third clock pulse to pass the what call this, the fourth digit, a fifth clock pulse, and then all the information will be here. Now I can have a control to read my information out, or I can pass my information further. I can have, look, if I'm going to get all the information in series, it means I must have, if I now, after 4 clock pulses, my data will be read. Let me say it was that example. After 1 clock pulse, the 1 will be here. After 2 clock pulses, I'll have 1 and 0. After 3, I'll have 1, 0, 1. After 4, I'll have 1, 0, 1, 1. That's the information I want to need, and I want to take it parallel. I can now pass my information out with the control, and it can go out. We'll come back to that control a little bit later. Or I can need a fifth bit to what? To now pass the 1 was here now. If I pass it the 5th time, the 0 will come out. If I pass the 6th time, the other 1 will come out. If I pass the 7 times, I'll need 7 clock pulses if I'm going to take my information what? In series, right? If I'm going to take my information in parallel, I only need 4. I need them to just come to their positions here. But if I'm going to take it serially out, in that case, then I need to pulse and fill up here and pass further to access my information. All of the information is going to be taken in series. Then I will need 3 extra bits. After 4, I will still need a 5th one to pass the 0, a 6th one for the 1, and then what? Another a 7th one for the last one. So you have to be very careful. I think I will explain this when I come to the timing diagram of this particular one. So this is the one case where we are passing information to the what? We're shifting our information to the left. This is our left shift. The alternative is to what? Is to do a right shift. All right, I'm gonna superposition my other diagram on this one here. All right, so that people can relate to the difference. If someone wants to go back and think, you can pause the video and go back and listen to whatever you didn't get. But for now, I want to explain the right shift on this same space so that people know the difference. All right, the first thing is, all right, all right, before I go there, I did say that you could use different flip-flops. Like I could, instead of a D type, you could use a JK. How do you do that? I could take a JK, but I want it to work as a D. So what I'll do is I will have my input going in at the J, and I need to invert. That's how we convert a what? We've done this before. We need our input to what? Our J input to be inverted for the K, so that what? The JK behaves like a what? Will act like a D type. Obviously, the clock will still depend same. If it's a what? If the JK is a if it's not a master slave type, then it will be direct. But then if it's a master slave, we'll have to what? We'll have to have our clock done the same way, all right? As for other master slaves. Now, then I will need this to obviously pass information through to the next one. If we are using, we have the option of what we can mix. We can have this one being a D and passing through to a D, but normally when you do JK, we might do all of them as JK. I think it's okay to be consistent. If you are going to have mixing them around is not really clever unless we don't have a choice. All right, But let's say you are short. Let's say we have 3 D types and 1 JK. Wait, so then you are forced to mix. But then if normal circumstances, you would actually what? You would have your J's working together, so that will be your Q fitting the next J, and that will be your Q1. Okay. Now, however, remember that I need to do this for the next one? Do I need to do that for the next one? Do we need to convert energy? Remember, these are components, but these are symbols. But these are actually what? These are actually circuits, all right? And these circuits are made of components, and the components cost money. So it's not wise to just to put circuits, extra circuits in building circuits, extra circuits when you are trying to build our systems that are actually going to be what redundant and actually cost us money. Why am I saying this is redundant? Remember that we are trying to, all we are doing here is trying to invert the Q, okay, or the input to the J, all right, which is the Q. But remember, we have a not Q output here, and that not Q already does that job. So we really don't need to what? If we are going to use JKs here, we do not need to have extra and an unnecessary number. This one is unpreventable. There's no other fit. The data is coming in here. This is the series input. So the series input is coming in there. Let me rather call it input. The input is coming in there. So there's nothing to invert. So here you need the inverter. But in this case here, you already have an inverse of that output, so you might as well call what, replace, instead of having what, an actual circuit that's going to cost extra money. Remember, if it's 4 circuits, you're going to need between each and every one pair, you're going to need a what, you're going to need that circuit. So where it's not necessary, it will be actually an expense that is not warranted. So what you then do is you remember, it will be good to remember that the Q and the not Q are already inverting each other. So you just take your what, your K from the what. So this JK here is configured, is thus configured as a D type, even though there's no physical what? There's no physical inverter there. But because that output there, that not Q is an inverse of that, it behaves, that input is now behaving as what? As if the input to J is inverted. It's not behaving as if the input to K is actually what? Is actually the inverted input to what? To J. Because Q and not Q are what? Are inverses of each other. So sometimes it saves, it helps you to be a little bit what? To be a little bit clever and not create situations where your circuits end up becoming what. Remember, in designing circuits, cost has to be taken into consideration as well. So those unnecessary what, those are fitting in unnecessary what, unnecessary inverters here would add to the cost. All right. So, but what I meant there is that other types could have been used here that are not D, as long as they are configured by D. This is what we actually meant. This is configured as a D. This is configured as a D. So it's actually working as D's. All right. So, but so what you're saying is the type of flip-flop that is needed for what, for shift register, is a D type. All right. If you're not going to have a D type, whatever you're going to use has to work as a D type. That has to be emphasized. I cannot emphasize it enough actually. So now, suppose the same question came and you said, okay, fine, you are supposed to use, you don't have JKs, you don't have D types, and you've got SRs. If you have an RS flip-flop, you will still need to convert that RS flip-flop into a D type. In any event, this is how the D type was built in the first place. So by what? By converting the input of the what, of the SO, this is basically going to work as what? As a D type now. So again, you don't have to what? You don't need to have extra inverters because the Q and not Q are doing this job there. All right. So again, doesn't matter which flip-flop. So we can in tests. You can be asked what? To use D-type flip-flops. You can be asked to use other flip-flops. You have to remember, if it's other flip-flops, the configuration of those flip-flops must be seen to be what? To be called to be D-type. All right. So that aside, I will then show how we can do a what? How we can do a right shift in the same space so that we save ourselves what's called. I don't know whether I should remove this. I think if people want to think, they can replay. So what I'll do is I'll say, okay, so if we are going to want to go to the right, if we are going to change direction now and go to the right, this will no longer be a what? This will no longer be a left shift, it will be a right shift. So the opposite becomes true, right? The opposite becomes true, right shift. Okay, now data goes in, it does not go in at the right anymore because we are shifting to the right. It goes in at the what? At the left. Okay. And what does that mean? This is no longer the MSD, this is the LSD. Okay. Our data for the right shift, it does not go in at the right. We are shifting towards the left. We are shifting towards the right shift shifts towards the right, sorry. So we are going in at the left, which is the what? Which is the, I said not LSD, and I still wrote LSD, which is the MSD. The left side is the most significant side. That is where we get our most significant digits. So our data is going to be input at that end. And then does it glide toward the left? No, it's the right shift, so it's going to glide towards the right. So this is no longer true. I'm just showing you that it's very silly to not remember this because it's actually just opposites. Okay, so this is now going to glide towards the right, and the right is where you get the LSD. So our data is now going to glide towards the right. All right. Then obviously the LSD doesn't lead anymore. That does not make sense for the LSD to lead anymore. What leads now is the LSD. The LSD digit will go in first. All right. So if we are going to have this example, the LSD being 1 is going to go in first, followed by that one, followed by that one. Remember, they are going in that direction. So when you are done, that one must be at the furthest end. So it must go in first, followed by that one, followed by 0. So it's very important. This is going to be very important when you're doing what? When you're doing the what called the timing diagrams for them, shift registers. Okay, that information is going to be very important. So I'm doing it in the same space so that people can get a gist of what we're talking about. So what does it mean? Our data doesn't go here anymore. Our input is no longer here anymore. This is our output now. Okay. Our input, remember I said everything is now opposites. What was the output is now the input. What was the input is now the output. So our output now, where we had an output for the left shift, we now have the input for the right shift. The series input is there. Now this one will be the output. We had an input for the left shift, for the right shift, that is the output. Okay, now is the clock still common? Yes, they still have to open at the same time, so that doesn't change. The clock will still be like this. If the clock, if we are using what the D latch, then it's going to be what? It's going to be a direct. If you're using master slave, then it's going to be that. That doesn't change. Okay, that part doesn't change. And also we are going to need to first reset our information. That part doesn't change. We're going to need to reset the information so that what? So when you start with fresh information, no rule against it. I mean, unless it's going to what? Unless it's going to cause a confrontation of data. But otherwise, it's not really strict. You can pass the data out. It will still work, but it's safe to what? It's safe and good practice to what? To clean it out first. So therefore, our reset data, our set data is still redundant. Okay, but then now, and the not queues are still redundant. But then now what's important now is that our data does not pass from between two what call this, between two flip-flops. Our data doesn't come from the what? From the right to the left anymore. Our data now moves from the other direction. So our data will not move this way. Our outputs will remain our outputs, no harm. Our queues are still our queues, no harm. Our queues are still our queues. There's nothing wrong with that. Okay, but our data, our series input doesn't go through. Remember, our input does not go through a what? Does not go through a, what am I doing? Does not go through the Q, but our input goes through the D. So our input is going to go through, our series input is going to go through the D. Okay, come out at what? I'm going to have to move that reset data because it's going to be in my way. I can see that, so I'm going to put it back. But our input now is going to what? Come out at Q, at the first Q. It goes into the first one, comes out and goes into the second one, the next one. Maybe I shouldn't have to do that. Let me really not worry about this. Let me go at the top. So I will go from this one, it goes on to the next one. Okay, now it will come out of that one and go to the next one. So what do you see now? The one to the left is fitting the what? The one immediately to the right of it. Okay, so it goes into a D, and that one then now will come out. Oh, why do I have to do that? I will take it there, and it will fit the last one. Okay, and this can be our well, and I was wrong to call that an output. Okay, the output is not at the what? I almost made a similar mistake here. The output is not at the D's. Need to remember that our output is at the what? Is at the Q's. So our output is actually at the Q. So our output here is the final Q. This is our series output. Okay, so this is still our parallel output. If we clock this 4 times 4 bits will go in, and then we can control and take that out and take the parallel output. But if you want to take the output 1 bit at a time, we have to clock 3 more times for what? For this kind of data. We have to click it's always you click one less time than the number of bits you have to put in to get the series data out. So let's suppose this was a 5-bit number. I would need 5, but then to take my series data out, I would have to click 4 more times if I'm going to take my data out in what in series. Because if I was clicking in, let's say 110, I would need 5 of them. So when my numbers are now lined up to, I will have my what? My 1 there. To get the second one, I'll need to click an extra time. That is a 6th time. Then I'll get my next one. To get the second, the other one, I'll need to click an extra time. To get around there, I'll need to click an. So you see that I'll need to click. If we're going to take the data in serial, we need to click 4 more times than we would if we're taking it in what? In no, not 4 more times. We need to click it. We need to clock our register 1 less time than one less time, not 1 less time message. If I say 1 less time, it sounds no, it's actually wrong. Look, let's make it. Let's say you've got n bit flip-flop. What was this? Shift register. All right. To get the data out serially, to get the data out parallel, you have to click n clock pulses. All right. Now, to get the data, this is to get it parallel, in parallel, for parallel, okay, for parallel. All right. But for series, you have to clock it n plus n minus 1 times. All right. I think mathematics makes life easy. All right. Extra. All right. For serial. All right. For serial. What do I mean? If I clock the first time, let's go back to 4 because I don't have a 5 to make an example with. Let's go back to 4. If I clock 1 time, the 1 comes in. Okay, this 1 comes in, the LSD comes in. Remember, LSD comes in first. All right, LSD leads. So I clock again, the LSD moves this side, the second one comes in. If I clock again, the LSD moves that one more, that one follows, the other one comes in. If I click 4 times because there's 4 bits, then we've got our first bit out, and then in this case here, the least significant goes out, the second one, the Q2 goes out. They're not going out, they actually, after 4 times I'll have my data sitting in its positions 1 0 1 1. But this is, now I can get my data in parallel. I cannot get it in series. I can only get it in parallel. Now to get it out in series, I only have the first one in series. Okay, so I need to clock it an extra time to get the second one, for that one to follow. I need to get it an extra time for that one to follow. So obviously I need to clock it as many times as I have left, and that is obviously 1 less. Okay, because I was already having the first one. So I have to clock it. So if there were 4, if there were 4 extra here, I'll have to clock it 4 times to get out the last one. So obviously that's why I'm saying n. Oh, this will work out to what? To 2n minus 1 again. So we have to click it n times for n for what? N clock pulses if you've got an n bit serial register. And then I hope I didn't make it too confusing. I did get my tongue twisted a little bit, so probably people might have unfortunately fallen off. But it's easy enough to understand. These are what you want to note here. What is most important here is that with this with the what with the left shift, we entered at the least significant side and we glided towards the what the most significant side. For the right shift, we are entering we are entering at the MSD and gliding towards the what the LSD. That is basically the gist of the right shift and left shift registers there. I hope that was informative. I hope the tongue twisters didn't twist the brain as well. So with that, let's meet when we're doing that. I want to proceed next to do the what? To do the timing diagrams for this. Probably they will clear up what we're talking about. Alright then. Thanks so much. Ciao. I hope you enjoyed.